Today we're going to continue on our series in regards to population growth and how it relates to first order differential equations. And this time we're going to kind of extend on what we worked with last time, that being logistic growth, but this time we're going to work with a threshold. Alrighty, let's get right into it. We'll first discuss the model and what's changed. You'll notice the logistic growth model kind of embedded within this logistic growth model with a threshold that we have here. The only difference being that we have this 1 minus the population over the threshold term being multiplied by everything else that was there before, and then you'll also notice that we have a negative sign in front of everything. And the reason we put these in here is because what we want to happen is we want our population to not change as our population is approaching the threshold. So as our population grows up until the threshold, then our population will not grow anymore. Or if we have our death rate be much greater than the birth rate, then as our population approaches the threshold, our rate of our population's change would become 0 again as well, meaning that is an equilibrium solution. And then we put this negative sign in here, and it'll be a little bit easier to see why we have that negative sign in there in a second, but we put the negative sign in there so that it's easier to see on the graph what's happening, because if you don't put the negative sign in there, then things are a little bit backwards. Okay, let's continue. We'll go ahead and first solve this model and try to make sense out of the different pieces of information we've been given. This one is a little bit more complicated and not as easy to work with, since we're going to have to leave our answer in an implicit form. And we're going to have to use a lot of numerical techniques or get help from a computer in order to really get some significant results from this critical threshold model version of the logistic growth model. And so, okay, here's our model right here. I'm going to solve this just like we did the other ones as a first order nonlinear separable differential equation. Okay, so I'm going to divide p times 1 minus p over k times 1 minus p over t on both sides, leave the negative r on the right hand side, and multiply by dt, after which I'll integrate on both sides. On the right hand side, I'll just be left with negative rt plus c after I integrate, and you'll notice that on the left hand side what I've done is I've combined the 1 and the p over k and the 1 and the p over t. And then I've also factored a 1 over kt out of the denominator and then brought it into the numerator. And my whole reasoning behind this is so that it'll be easier to simplify later on. This requires me to use partial fraction decomposition if I want to integrate that term on the left here. And so I'm going to set it up like this. Kt over p times k minus p times t minus p is equal to a over p plus b over k minus p plus c over t minus p. I'll multiply by that denominator on both sides to get that kt is equal to a times k minus p times t minus p plus bp times t minus p plus cp times k minus p. And then I'll choose a convenient value for p so that I can go ahead and simplify a little bit. You'll notice that if I let p be equal to k, then 2 out of the 3 terms on the right hand side of the equal sign will cancel, and I'll just eventually be left with the fact that b is equal to t over t minus k. Okay, and then if I plug that back in and simplify a little bit on the left, notice what I've done is I plugged it in and then I've subtracted it over to the left. I'll leave the extra arithmetic there to you so that you can see that a k minus p eventually will factor out. If I do that, then I can divide that by everything on both sides to leave myself with this expression, and then I can pick another convenient value for p to find another variable. I'm going to pick p equals to 0 so that I can isolate for a and get that a is going to be equal to 1. Okay. Awesome. Okay, just give me 1 second. And then from here, what I'm going to do is I'm going to do the opposite, right? So if I let A be equal, well, rather, if I let P be equal to T, then the other term is going to cancel out, the term with the A in it, and I'll be able to isolate for my C to get that C is equal to negative K over T minus K. Again, I'm going to leave the extra arithmetic to you for this model here, just because this one takes a little bit longer to write out, and we didn't have quite as much space here on just this one page. But eventually, what you end up with is you end up with the integral of 1 over p dp plus t over t minus k, the integral of 1 over k minus p dp, minus k over t minus k, the integral of 1 over t minus p dp is equal to negative rt plus c. Alrighty, and then from here we'll integrate each individual piece, and then for the two inside pieces, you'll notice I put a negative sign in front of them, as we're gonna have that negative dp as the derivative of the denominator there. Okay, and then once we've reached this point, we can bring that t and that k into the exponent and write everything in terms of just one logarithm, and that's going to kind of work like this. I'm going to have p to the power of t minus k times t minus p to the power of k over k minus p to the power of t, and then you'll also notice that I've brought the t minus k, which was in the denominator on the left, over to the right hand side first before I exponentiate it on both sides to get rid of the natural logarithm and bring this c out to the front on the right hand side. And then if we apply our initial condition, that being that our population at time 0 is equal to p0, then we're left with this as our constant. Okay, so this is our model in the simplest form we can put it in at this time. There's no way for us to isolate for p, unfortunately, as a function of time, as nice as that would be, as this is technically going to form the graph of a relation. It does not pass the vertical line test, and it makes sense because our population is going to behave rather differently along these different equilibrium points that we have here. Okay, let's move on then to working with a specific example. Okay, suppose I have a population of deer in a specific environment that will double in size over 2 years, and that is if there is no restrictions on the amount of resources available. Then let's also say we have some environmentalists predict that the amount of resources available in the environment will only be able to sustain up to 100 deer. Let's also say they predict that the population cannot survive without a minimum of 20 deer present. And then if there are initially 25 deer, how many deer will there be after 4 years, and at what time will the population begin to increase at a slower rate as it gets closer to the carrying capacity? Okay. Now, what I'm going to do is I'm going to list off what we know here first. We know that we have an initial population of 25 deer. We know the carrying capacity to be 100 deer. We know that there is a threshold of 20 deer that need to be present in order for the population to survive. And we know the proportionality constant r to be the value of the natural logarithm of 2 over 2, which just comes from the standard population exponential growth model, since it said they would double in size if there were no restrictions on the environment at all. Okay, so that's going to be the value we use for r. This is going to yield us this equation right here. That's our model for our situation. And this is the corresponding differential equation that will go along with that. That'll be more useful in the long run here, and we'll discuss why. But what we're going to do right now is we're going to go ahead and answer the question. Sorry. So this is the graph of our function. Here I've graphed it using some powerful utilities. And the reason I say come up with the graph using a computer of some kind is because it's very difficult to find a value which will a value for p which will satisfy our condition when t is equal to 4. So if you look at this graph, as t goes to 4, then we get around approximately 41 deer present after 4 years have passed. Now that's definitely not double of the initial population that we began with, 25 deer, and it's definitely been a lot more time that's passed. And the reason being is because as the population increases, the amount of resources available in the environment is being restricted, and so our population is growing at a different rate. Okay. Then what we want to do after this is we want to take a look at some inflection points. And so what I've done is I've taken that same graph that we just looked at here. I've plotted some lines that represent the equilibrium values, 20, 0, and 100. You can find these by just setting the derivative equal to 0. And then I've also put some open circles on here, not to represent that the graph doesn't include those points, but just to make it a little bit easier to see the inflection points on our graph, which is the point where our graph is going to change from concave up to concave down, or concave down to concave up, meaning that's going to the point where the rate at which our population grows begins to change, because our proportionality constant changes with respect to time in logistic growth. Okay. Now, how do we find these inflection points? It's a little bit tricky, but what you need to do is you need to work a little bit of chain rule magic here, right? Since we have dp dt already, if I want to come up with the inflection point, I need to set the second derivative of p with respect to time equal to 0. And so what I've done is I've differentiated with respect to p, dp dt, which is what we have already. And then I've also had to multiply it by another dp dt if I do that. And the reason being is because p is a function of t, and if I differentiate it with respect to t, then I need to tack that on. That's how implicit differentiation will work. This, you'll notice, cancels to give us d squared p over dt squared. And if I let the right-hand side of my differential equation be represented as f of p, then I'm left with f prime of p times f of p is equal to 0, where f of p equals to 0 represents these equilibrium solutions that I've graphed here with the dotted lines, and where f prime of p equals 0 is going to represent the possible inflection points on our graph. Now, if we take a look at our function right here, our model, I should say, and then differentiate with respect to p, the right-hand side of the equals sign, we get that our inflection points can be found by p is equal to k plus t plus or minus the square root of k squared minus kt plus t squared over 3. The k plus t plus the square root is going to represent the upper point of inflection, and the k plus t minus the square root is going to be representing the lower inflection point. The question that we were dealing with, and I should also mention this 3p squared plus negative 2k minus 2tp plus kt equals to 0 line translate to the bottom line here by just applying the quadratic formula and isolating for p. But our question was asking at what point does the rate at which our population grow begin to change? And we can answer that question by finding the x value that corresponds with this point of inflection up at the top here. So what these equations we've got here are going to give us is they're going to give us the y coordinate. So the population at that point in time, they're going to give us the y coordinate. And it begins to get very difficult to come up with accurate values for t when finding points of inflection in this model. And so what I'm just going to say is I'm going to say that once you've plugged in your carrying capacity, your threshold population into this formula that we've got below for the inflection points, keeping the positive one, and then plugging that one back into our differential equations solution and solving for x using a computer, we'll find that after around 6 point, I believe it was 0.15 years or something, our population will begin to change. It might be a little bit more than that. I can't remember the value exactly. I had it written down somewhere, but it's around 6 years that it will take in order for the population's rate of growth begin to change, right? And they'll start to level off towards that 100 deer carrying capacity for that environment. Obviously this example isn't super realistic, but you can see when applied in a world where we have supercomputers, this can be a very powerful tool to help us estimate the amount of time an endangered species might have, for example. This is something that this model is often used for. That's about it for today, though. Let me know if you have any questions. Send me an email, send me a text message, and yeah, talk to you later.